In this video, we are talking about capacitors, capacitance, how capacitors behave in a circuit, as well as talking about dielectrics, which alter the properties of capacitors. First things first, what is a capacitor? So a capacitor is basically just a set of parallel plates which store charge, can store and discharge charge in a circuit. So what do you know about parallel plates? We know that each plate has equal magnitude of charge, but opposite sign. Right? So I'm not too sure how I would explain this. We can try like this. So this is a voltage source here. And if we had this connected to a capacitor, the flow moving through it would create a positive and a negative terminal, right? So if we break our connection in that circuit, so after we've charged it, so after it's been closed, if we break that circuit, this capacitor is still going to hold on to its positive and negative charge. And now, if we close that switch again, with no voltage source, actually no, sorry, if all our voltage has been used, if we close the switch again, then that last bit of charge is going to dissipate and it's going to flow out. I'll put a link to the lecture that I got this material from. In there, she does a FET simulation about capacitors, so you can visualize it in a more comprehensive way. But this is the most, I guess, straightforward way I can explain it. So there's a new equation that we're going to introduce for capacitance. And this is basically just the capacity of a capacitor, so its ability to hold charge. And it's going to be constant for a certain system, right? So is constant ratio. So you're going to see how this is in an example question. Capacitance is represented by charge over our potential difference. So this is the main equation that we'll be using for our problems. And we know that our potential difference is equal to voltage of two places, where it's the integral of our electric field times the path that a particle takes. Okay, so looking at this example here, this is a different representation of our our potential difference. So from previous videos, we know that our electric field between two plates is given by charge over epsilon times the area of one plate. And we want to get this into our Cartesian form. So we know that electric field points from positive to negative. So because it's pointing downwards in our z direction, so that we give it a k hat unit vector, make that look more like a k. And this is negative because it's pointing down. Okay, so we know capacitance is equal to our charge over our potential difference. So how would we translate that to this problem? Okay, so we know that this is equal to from d to 0, right? Those are our separation distances. and it's E dot ds, but instead of s, I'm going to put z because we are only traveling along the z axis. Okay, so now when we write capacitance, this is charge over our integral. Right, and since our, actually no, let's just start only with our potential difference first. So this dot product goes away because the path that the electric field takes is just directly downward, so it's completely straight. So because of that, we can get rid of our dot product. So we're going to keep our integral, and now subbing in for our E value times dz. And since this is constant, we can kick this out. So this is negative q, sorry, it's positive q. Right, there's supposed to be a negative in front of this integral. I apologize. And our integral of dz, which just turns to our distance, right? So we just have z, and z, when we plug in for distance, is q d e naught over a. And when we put this into our capacitance equation, this is q d epsilon area. This is equal to so these two cancel. So this is 1 over d, and this is just a reciprocal, so let's change it and flip it. And this is our final equation for capacitance of two parallel plates. In our next example, we are going to be talking about spherical capacitors. So we have a sphere inside and a shell that surrounds it. And we want to derive an equation for the capacitance of the spherical capacitor. So let's start by finding our potential difference. And we know electric field is directed from positive to negative. So these are going to be directed radially outwards. And we know our equation for this electric field is given by 1 over 4 pi epsilon 0. Our charge, because the charge quantity on both these is the same, r squared. So when we put this into our potential difference, so this is represented by the negative integral from our starting point. So let's call this a here because we have our smaller radius a and our larger radius b. This is going from a to b radius. And then we're going to put our electric field in there. And since this is a spherical one, it's directed radially outwards. And this is times the dot product of dr. So this is our change in path. And since it also follows a radial path, it's our change in radius in our radial direction. Now, electric field is constant all the way around. There's going to be no dot product. So once we get rid of that, we're given negative a to b right, and we're going to get rid of our direction vectors now that it's just scalar multiplication. Okay, so this whole term is constant, so we're going to kick that out. Times q over r. Sorry, just this first part is constant, and so is our charge. So charge is also going to come out, but in our integral is going to be 1 over r squared dr, When we integrate that, that gives us so this is r to the negative 2. I'm going to increase it to the negative 1 over negative 1. So this negative r at the bottom. And we are doing from limits b and a. Continuing to write this out, this is, okay, so it's negative 1 over 4 pi epsilon 0 q. And this is negative 1 over b plus 1 over a. Or you could say 1 over a minus 1 over b. Okay, and in our capacitance equation, this looks like, so this is q over negative 1 over 4 pi epsilon naught times q. These two q's are going to cancel, and this is 1a minus 1 over b. It's going to turn into, so let's flip all of these around, and this becomes a minus b over 4 pi epsilon naught. Sorry, this is wrong. So since we're working with the magnitude, this negative sign goes away, and this is 4 pi epsilon naught a times b over a minus b. All right, so that is capacitance and capacitors. And now this is taking us back to our electrical 225 course. So when we have capacitors in series, we're operating using Kirchhoff's law. Which states that our voltage total is equal to V1 plus V2 plus V3, whatever, equals 0, right? So in the case where we have several capacitors in the same enclosed loop, we want to know what the voltage of these are. So using the equation for capacitance, isolate for voltage, that is equal to Q over C. So in this circuit, our charge is constant, and we want to assume some direction. So if we're traveling in our loop going upwards, going uphill, this is positive, and then going downhill would be negative. So if we were to write this out, this would be V input. So let me write this so it's a little clearer. This is equal our A input. So first one. Then plus this one. So this is in our downwards direction. So we're going downhill now. So that's minus Q over C1. And we're still going downhill in this side in our loop that we drew. And this is minus Q over C2 equals 0. So therefore, if we were to add up all of our, if you want total capacitance of a circuit, they would have to do 1 over C and take this to the negative 1. Okay, so that's our adding rules for if they are in series. So our total C, our total capacitance is equal to our sum of all of our 1 over capacitance to the negative 1. Now, if we are in parallel, we are going to be adding just as is. So it's just the sum of each individual capacitance value. And this is because if we drew our circuit example here, our capacitors in parallel, and we drew our voltage loops using Kirchhoff's law, each one would be the same. So V1 would equal V2 would equal V3 in each window pane of our system. So because of our equal voltage, that's why we will be adding capacitor just as is when they are in parallel. Okay, so let's make an equivalent circuit. So we had some practice with this in ENGG 225, so this should be kind of hearkening it back to you. Okay, so we have parallel circuits here, so we can start by simplifying those. So we're going to start with, keep our 4 here, and we're going to change these ones out. And it's going to be parallel with our new 2. So we're going to add them together, and these are in series. So our series rules, we know are C equals -1. So if we do it for 3 and 2, this equal to 1 over 3 plus 1 over 2 to the -1. So this is 1 divided by 3 plus 1 divided by 2. And this is equal to 1.2. So this is 1.2 here. And if we did the same for this next one here, this is 3 and 1. So C is equal to the sum of, it's equal to 1 over 1 plus 1 over 3. So 1 divided by 3 plus 1. And this is 0.75. And now that we've got our whole system in parallel, then that means our total capacitance, we're just going to be adding each one up. So this is 4 plus 1.2 plus 0.75 plus 2. And our total capacitance is 7.95 picofarads. Right, that is our equivalent capacitance. Next, we are talking about energy stored in capacitors. Okay, so here we're introducing a new equation. And when we simplify it down further, we realize this looks a lot like our spring kinetic energy. So yeah, we're going to be using this equation to find energy stored in a capacitor using our potential difference between the plates and the total amount of Q that is on the plates in that moment that is stored. Okay, so talking about some unique geometries for these different applications. The energy density for a capacitor that has volume would be our potential energy over its volume, and that is in joules per meter cubed. So when we go about this, we would have to take our energy equation and we'd put it over our volume, which is our area times the distance it occupies, because we consider this as one object. We consider like our system of parallel plates to occupy this amount of space. So if you were to shade in this region, that's where the density comes from. So we know that the capacitance for parallel plates equal to epsilon naught A over D. So once we put it into this equation, we see our A's cancel out, and that gives us our energy squared over distance squared. So that's why we put the brackets around them and then just put both of them to a power of 2. And that gives us an equation that looks like this, where our potential difference over our distance is equal to our electric field. Right, so energy is stored in the electric field that it creates in between them. Next up, we're going to be talking about dielectrics. If you have two parallel plates as such, a dielectric is a substance placed between plates to alter electric field or the capacitance. So if we were to insert a dielectric in between these two plates, it could change some of the properties that we would expect a shape to have. This capacitor to have. So there's different kinds of dielectrics. There are polar dielectrics, which are polarized and have a positive and negative end. And when they're placed in the electric field, they orient themselves to point in their appropriate directions, right, with the positive end pointing with the arrow, negative end at the tail. Right, so this alters how easily the electric field can pass through to the other parallel plate. And you have non-polar dielectrics. So these are more like atoms, where you'll have a negative shell surrounding the positive nucleus. And then the nucleus and the electrons, kind of hard to see. So the electrons kind of just move closer to the back and displace the positive end more further. But in either sense, dielectrics alter the way that electric field passes through. So in this example here, a parallel plate capacitor whose capacitance starts out with 15 picofarads is charged by a battery with a potential difference of 12 volts. And while keeping the battery connected, the porcelain slab is slipped between the plates, so this is our dielectric here. And when I calculate the potential energy stored before and after the dielectric is added. So before, we're just going to use our standard equation that we started with, and this is going to give us 1.08 times 10 to the negative 9 joules. Right, so that's just plugging in for our capacitance and potential difference. But afterwards, we are using this equation. C of our dielectric is equal to our dielectric constant. So we have a table that shows what our value is for our certain material. So in this case, we have porcelain, and if we look at our table, it's 6.7. And we're going to multiply that by our given capacitance. So capacitance, like we said in the first part of the video, is constant in a system. Is not going to be constant in this case because we have a dielectric which is altering its capacitance. So then we're going to take our initial capacitance and multiply it by our dielectric constant, which is our K. And that gives us this new value of 100.5 picofarads. So then we're going to use this new value in our equation. Same equation as this one, we'll just have a different value for C. And this gives, so I didn't finish the calculation. So let's do that. 100.5 times 12 squared. And this gives us this is times 10 to the negative 12. And this gives us 1.44 times 10, 8 joules. So this increased by a factor of 10. So we can change the amount of energy in our system as well with our dielectrics. Okay, so that brings us to the end of the notes section part of this video. Join us in our next video where we'll be going through some Wiley Plus questions that relate to dielectrics and capacitors. And yeah, I'll see you in the next video.